Let me recall very briefly what we discussed yesterday, and we finished with the Jansky after having shown several applications of fluctuation theorem on different systems, and having done a small exercise on the blackboard. We discussed the point of Jansky equality, and just to fix the idea, so is the Jansky equality. It's a very useful method that allows you to compute, to measure the free energy difference between two states with protocols that can be as fast as you want. Okay, and so this really very different to what we learn in standard books of thermodynamics, because as we know, I mean, in order to measure correctly the free energy difference, you need to do quasi-static transformation, and then the work will give you to go from a state A to a state B will give you the free energy difference between the two states. Okay. But now the Jansky equality, okay, instead of doing only the mean of the work, you do the exponential of the work, which is a fluctuating quantity, as we said, because we are talking about a small system since several days. And so the result of this average tells you that you get the free energy difference between the two states, okay? Now, associated to this, okay, then the standard point that we already discussed, that indeed for Gaussian distribution of the work, the Jansky equality reduces to only a relationship between the fluctuation, the mean of the work and the variance of the fluctuation of the work during the process, okay? So the other important equality, which is actually related, as we have shown yesterday, to Jansky equality, is the Crookes identity. And actually, each time you can perform a transformation from A to B and the backward transformation to B to A, okay, this is certainly the best that you can use, because you have full information of the probability distribution functions of the work. And what tells you the Crookes equality, that is the probability of having the work done in the forward process to go from A to B with respect to the probability of the reverse process, the work done minus in this direction, you know, this is just equal to the exponential of the dissipated energy. And okay, and then you see that is very simple exercise to see that because of the normalization of PR, the Crookes equality is related to the Jansky equality, okay, by integration. Okay, is this clear? So then I gave you a simple example on a simple system. Was this always my torsion pendulum that is described by this equation? Now we apply very fast torque to the system that drive the system from this state, that is the state A, to the state B, okay? And then you see that the transformation here is very, very fast with respect to the relaxation time of the system, okay? And in spite of that, you see that when I construct the probability distribution function of the direct and the reverse process, you see that they cross at in the middle. And you see that indeed the crossing point, as indicated here, is very close to the free energy difference that you can easily compute between the two states in this system. Okay. So this was a nice experimental exercise But Janskinski equality has been used in many measurements. Probably I used the historically transparent slides. No, this was a later experiment. So what they did is, guys, this shows really the power of this equality that has a very strong application, especially in biophysics. And so the idea is the following. Suppose that I have I have a DNA hairpin, okay? And then using some DNA handle that biologists are able to do that are more stiff of the hairpin. What we do, we take the two extremes of the DNA and we glue using this DNA handle, one on a pipette, okay, and the other is a colloid in which there is this handle, and the colloid is trapped in an optical trap. Now the pipette is fixed. The optical trap, as you have seen, I can move by moving the laser beam, exactly as I was doing. So by measuring the position of the bead inside the optical trap, okay, the same thing that I did last time. Imagine that the optical trap is just a spring. So the position, the mean position of the bead inside the optical trap, in somehow is measuring the length of the spring, and so in this way you can you know the force that is applied to the hairpin. Unfortunately, I forgot to put here the time behavior of the system. So what you do now, you keep the pipette fixed and you begin to move or vice versa. This doesn't matter. So you increase the force and you separate the hairpin, okay? And then you measure the work that is needed in order to separate the two brains, okay? And so these are different. This is different realization, very fast realization, very medium speed. I can change the speed in which I'm stretching the system, and then you see that is remarkable here. That indeed you see independently of the speed, you see that the PDF of the backward process and the direct the forward process, you see they cross almost always in the same point, showing that indeed the error of the crossing point is not very large, and so this allows you to measure directly the free energy of a DNA hairpin. Okay, so this is a remarkable measurement. Many other measurement has been done in this, and now is a common tool actually in order to do such a kind of measurement. Okay, now let me. Do you have questions about that? No questions. Okay. So now I've shown to you several applications, and what I want to show you is another game that this will apply to the fluctuation theorem. Okay. Still, I will take an example taken from biophysics, and okay. Now suppose that I want to measure the power of this motor, biomotor, doesn't matter anyway. So it's a motor. I will not describe how it is. Anyway, you have, as in standard motor, you have a rotor and then a static part where there is, in this case, the chemical that allows the system to rotate, okay? And now what usually is done in order to measure the power of this of this motor, for example, as a function of the kind of nutrients that you put and the kind of chemical that is around the system. Okay, so what biology do? They stick this motor on a plate, okay, and then on the other side they stick a bead, okay. Typically, the drawing is thought to be in scale, okay? This is much smaller than this, but this is just an example. So you take a polystyrene bead, usually of 1 microns of diameter, okay? And so what you do, you observe with the microscope the motion of this bead, okay? So you look at that. What you do, you look at the mean velocity of the bead. You divide it by the viscosity that you obtain from the Stokes law, and at the end of the story, you get the torque that is needed, that is produced by the motor. Okay. But now you see, in principle, what you have again, you have here. I describe again the motion of the bead using a Langevin equation. So theta is the position of the bead on the circle. So this is gamma theta down. This is the torque that is applied by the motor. And of course, I have thermal noise that is due by the fact that you have inside the liquid. Okay. So this is the standard method. But now you have a lot of problem in doing this, and I will explain why. So first of all, gamma is rather unknown for several reasons. Because as we discussed the other day, you have the problem that this distance is not very well known because we are looking at the bead from the top. Okay, so as you know, the gamma depends also on this distance. And of course, depend on the exact measure of R, okay? So this is a problem because gamma at the end of the story of the bead is not very well known. Okay, so let us do, then, okay, so there is the shape because we assume that the shape is spherical, but of course, a polystyrene bead is not necessarily spherical. So you have a lot of errors in estimating these kind of things. So how you can manage? I will show there is a very elegant method in order to skip all this problem, and this is fluctuation theorem, okay? So what you do, let us suppose that I call this is my unknown, okay? And then what I certainly can measure very precisely is theta dot, okay? So the speed in which the bead is moving. Of course, this is a fluctuating quantity, as I said, because there is all the collisions with the molecules of the heat bath, okay? And so what you get, okay? At the end of the story, as you suppose a first approximation which is not completely wrong in certain regime of the motor, okay? You see that the work reduced to n, your unknown, times delta theta tau, that actually you know, okay? And so what you do now, you apply the fluctuation theorem, that being a Langevin equation, I've shown you that it works perfectly, okay? So you apply Langevin equation, and I write this. You remember, this is just the asymptotic behavior. This has to become 1, okay, for t that goes to infinity. Okay, and now you see that n, then this ratio has to scale as sigma tau n delta tau over kbt. Okay, and now what you can do? You plot this, okay, and you see that at this point, the real point, that the gamma disappear. Okay, you don't need the knowledge of the gamma. Okay, here. And what is happening here, you see that you plot the probability distribution, and then you plot the symmetry function, that is the log of the ratio of the two probability. And then you see this is a straight line. You do that as a function of time. You see that everything relaxes to a point, and this slope actually gives you your unknown without knowing any knowledge of the viscosity of the system. Okay, so this is very nice because it allows you to do measurements related to the fact that you are using just this theorem that you can get from stochastic thermodynamics. Okay. Now, okay, strictly speaking, there is still a small problem I will not mention because probably is a confusion. But there are, this is nice, certainly very good idea, but there are some hidden variables that one should know, but I will not discuss this point in order to avoid any confusion, okay? So, but this is an example in which you can use this, okay? And then I have another exercise that is very nice. Nobody did, but it works very well. Suppose that you are Millikan and you want to measure, as he did, the charge of the drop that is going down in his apparatus. Everybody knows the experiment of Millikan. And if you remember, one of the key points from an experimental point of view, again, in the case of Millikan, was the fact that the viscosity, measuring to have an exact measure of the viscosity of the air is very, very difficult. And also for the size of the drop, okay? And now, again, what is usually done. You measure this, and then you measure the value of the electric field that is needed in order to equilibrate the weight of the drop. But now you see that again, the weight of the drop is determined using the viscosity, which is a very, very, very difficult stuff. Okay, especially in air where the viscosity is very weak. And now, okay, let me do this simple game. Okay, what is the work? The work is just of the falling drop. Is just minus mg plus EQ, the external field that is applied from outside. Again, I'll do the fluctuation theorem. Suppose that I'm using this already on very long time. I put already the asymptotic behavior, and now you see that again, okay, this ratio is to be linear in X, okay, and just fitting the slope, I get immediately the mass and the electric field of my apparatus, and so I can measure immediately. No, the electric field already known, and the charge of the drop, okay? And so again, I can do the experiment of Millikan without any need of calibrating the viscosity. Question? Yes.
So in the Landauer equation, in this case, what is eta?
What?
What is eta physically?
The noise is again the fact that the system is again surrounded by air. So anyway, I mean, you have the thermal noise. No way, because you can put in a liquid, you can put in air. Usually you do in air because in a liquid is not a good measurement because of the bilayers that are forming around the colloids. So that's the reason why Millikan did this in air. But in any case, in air you have the collision of the molecules exactly as in a liquid. So okay. So, yes.
I think I lost track of the proposal. You're measuring what? You're measuring the distance traveled in
Yeah, definitely distance travel, exactly as Millikan did. I mean, I do anything different. I just measuring the traveling of that. But as I know that there are two forces that are applied, the work is just n minus mg plus aqx. Okay.
So you keep with the same drop you propose.
Yeah, the same drops. I mean, you can go up and down. You increase the field, and then you go again, and then you can repeat the experiment many times, of course.
I see. So you want, so x is the distance traveled in a fixed amount.
Yeah, exactly. Yeah. Or a fixed amount, yes, okay, or as a function of time, you observe it for a given amount of time, and then you measure the distance that the system works. So this is again is a fluctuating quantity, because X fluctuates, of course, from one test to the other. Okay. Okay. Other question? Okay. So there are other examples, but I don't bother you with all of this. For other system, I mean, again, you can use you can measure force again, that an unknown force, using the same trick of the linearity that allows you to do measurement really with reducing the number of parameters that you have to fit, thanks to the fact that you know that in this system the fluctuation theorems has to hold. Okay. So I will skip this. This is another example. Okay, no, I'll skip all of this. And okay, I just a word about this. This is a very difficult problem that I will not discuss. I will only mention. There are several persons in this hall who did a very nice experiment. I don't see Mahesh, that during his PhD thesis did some work about that. Then there is Menon that also did a very nice experiment on this sense, on granular media. And the idea is corresponds to the effects picture that I've shown the first day, in which the noise is not thermal, but is produced by the dynamics itself. Okay, for example, the shaken granular media, or in the case of Mahesh, was the turbulence inside the turbulence inside a volume of fluid. I don't want to discuss this because probably may perturb many aspects. This is a soft matter school, so it's not. But it's just to mention that several things can be done also in those system, granular system. But I prefer not discuss this in order to avoid to put too much material on this. So let me stop about this problem of the fluctuation theorem, and okay, I want instead to discuss another aspect of stochastic thermodynamics that is very important, and it is nowadays a very well studied problem, is the connections of stochastic thermodynamics and information theory. Okay, so let me change the slides, and okay, I'll do this. Okay, fantastic. So what I want to discuss now is a different aspect, and is the famous example of Maxwell, about the Maxwell demon, that produced a lot of discussions on many years. You will see. So this indeed this idea of the connection between thermodynamics and information actually apply in biophysical system when there are several reactions that are controlled by that. Okay, now this disappear anyway. Okay. Well, okay, I don't understand why he changed. Okay, doesn't matter. Anyway, this was an example, just not very useful. So the main question goes back to Maxwell. Okay. And the question that I want to discuss, is there any fundamental law of physics, thermodynamics, which connect energy with information, okay? And can we perform a logic operation with an energy cost? These are the two questions that I want to discuss, okay? And this these two questions that has been asked by very famous physicists. For example, Maxwell was the first, then Szilard, Brillouin, Shannon, Landauer, also Feynman wrote something about these questions, okay? And so in what is following, I will try to discuss first of all the second law of thermodynamics and how the Maxwell demons was conceived, and then I will discuss the Maxwell demon and the Landauer's bound, okay? Then I will explain what it is, the Landauer's bound, later. And then I will show you several experimental results, and eventually at the end, the role of inertia. And finally, the Landauer, the connections, this is very, very strong statement, because you can actually connect the Landauer bound to the Janskinski equality. You will see the connections. Now you learn about already between of Janskinski equality. Okay, and then the importance for applications. Okay, I will discuss just at the end. Okay, so let me start. Ah, no, sorry, this is a problem that I cannot work like this. Let me close. I know what it does. Okay, sorry. Reload. Okay, sorry for that. Okay, see that now it works. Okay, good. Okay, so we already said all of this. Okay, so we already discussed this point, and what is important here is to remember the formulations of the second law. And what is important, I want to stress this, because there are, as you know, there are many statements in which you can formulate the second law of thermodynamics. But what we are interested in is this, that okay, you can prove that all of them are equivalent. But what we are interested in is just this formulation given by Kelvin. Okay, and that this formulation says no process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. Okay, and so this is just the key point of the Maxwell demon. Okay, first of all, let me recall where the problem about connection thermodynamic is, and then I'll go to the Maxwell demon. Okay. We know everybody that in thermodynamics, this is the definition of entropy, where pi is just the probability of a microstate. Okay, this is what the formulation of Gibbs. And then the question is that in information theory, there is the formulation of the Shannon entropy that you see they have the same formulation, the same equation related. So, but the question that on people in which is fighting is thermodynamics entropy and is the same of information entropy. Okay, this is the real question. Okay, so let me go first of all to the Maxwell demon, and then you will see the relationship with this. Okay, so probably you know, but I mean, just to make a common language, what the Maxwell demon does, you start from a containers that is at a given temperature. So you have fast and slow molecules, and then you separate these containers into smaller containers that with separated by a gate. Okay, And now you put an intelligent object, an intelligent being, that is looking at the system, okay, and then is moving this gate by separating the fast and the slow molecule in such a way that you find all the hot molecules, so the fast one on the left and the slow molecule on the right. In this way, you have produced a difference of temperature. You can do some work, okay? But the problem is that you started from a single temperature. And at this point, you are violating the statement of Lord Kelvin that I just mentioned, okay? Because you produce the work starting from a single temperature, okay? With the reservoir on a single temperature. And then, okay, pay attention, the gate, actually, the motion of the gate can be done perfectly in a reversible way. The only problem is to reduce frictions, but in principle, the answer of this is not the work produced by the gate, because you can conceive gates in which you can open and close. For example, imagine that I have just a glaze that is just moving, that the friction is small. I mean, you are just compressing a spring, then the spring is giving you the work that you have produced in order to compress, and then you see, in principle, you have done any work on to stop the fast and slow molecules. Instead, there was the first who think that probably information could be the answer was Leo Szilard and later Léon Brillouin. Okay, so let me see. Yes, question. Okay, questions? No. Okay, so what Szilard think? He did a very, very nice idea, and he thought to a single molecule gas that was moving inside a container. Okay, now you see that the idea is quite simple. The daemon now has not to do many measurements. It has just to decide where the particle is on the right, on the left. Then you put a barrier with the weight, and then you see that the pressure of these molecules of gas is pushing the piston, and then you are doing work just on that. Then when the system is there, you may move the particle and then you start, okay? Now you see that this you can do cycling work. Okay, and so what is the problem? The answer of Szilard that indeed there is some quantity that you are neglecting is the fact that you're making observation, you're doing measurements, okay? And so all the energy that allows you, that you're introducing into the system, it allows you of not violating the second principle, is the fact that you are doing measurements and you are observing the system, introducing measurement, introducing information, okay? And then there was Brillouin, Landauer, and Bennett who did other conjectures about this. You will see. Okay, so the question is that now today, modern technology and stochastic thermodynamics allows us to design the real demons, okay? And then so again, as I'm an experimentalist, I will show you experiments and results about all these kind of things, okay? So one of the first example of this was done in a remarkable work by Toyabe and collaborators. And what they did is the following, in which they show the importance of information, okay? Look, the idea is the experimental system is rather complex. I will not describe, but the principle is exactly the one that is drawn here, I mean, in a schematic way. you have a staircase, okay, and you have a colloidal particle that is a small staircase, of course, where the particle is very sensitive to the thermal fluctuations, okay? And so the particle is submitted to thermal fluctuations and fluctuates, and then if you do nothing, the particle will go up and down, okay, and because of thermal fluctuation, in general, will go down, okay, on your staircase, okay? But there are instances in which, if the barrier is not too high, the thermal fluctuation is like the particle to jump on the other side, okay? And now, suppose that is here that the demon is coming. The demon is looking at the system, and if the particle goes on the left, it is climbing on the staircase, he put a barrier, okay? Now he waits again another good fluctuations, okay? And then he put a barrier again. And now you see that actually the colloids that is here is just climbing on the staircase, okay? And now you see that indeed the information here is quite simple, because if I take the definition of Shannon, you see you have only two possibilities: either you go to the right or you go to the left, okay? And now, so the information in this case is just P log P, where P is the possibility of moving, let's say, to the left, okay? And now there is something that you can prove. I will discuss eventually later, because I don't know whether I have enough time, but you can prove that indeed, in the case of feedback system, because at the end of the story, the demon is just a feedback that is acting on the system, you have to modify the Janskinski equality, adding the information that you are that are introducing into the system. And now you see that this equality imposes that the mean work is actually larger than the free energy difference minus KB Ti. Okay, this can be proved. I will show eventually later at the end, but trust me. So you see that from this equality, I can track this inequality. Okay, that is an extension again of the second principle, because you see the second principle tells us that the work that I do between two states of the system has to be larger than delta F. Okay, whereas here you see that the work can be smaller thanks to the fact if I introduce some feedback, some information into the system. So this tells really you that the information and thermodynamics is related, because if I introduce some information that I can measure, for example, using the Shannon definition, you can extract a work that is actually smaller than the free energy difference that of the state. Okay, is it clear? No questions? No questions. Okay. So the other important result I want to discuss is this. Okay, is the Landauer bound, because these are okay. This is a strong implication too, but okay, one has to make a choice. So I will prefer to go into this this description. Okay, and so I will discuss what the Landauer bound is. Okay, which is actually the counterexample of that. Okay. No, okay, already discussed this. There is not much more, okay, or what I already said in the other slides. Okay, so there are other examples in which experiments has been done. For example, in single electron transistor by the group of Jukka Pekola in Oslo, and then, for example, this is a very smart experiment, because somehow I'll give you just, I don't go all the, but the idea is that here you have, this is done a low temperature experiment, so they have a very excellent control of the amount of heat that is transferred between the system. And actually, what I've shown here, it is very beautiful, that when the demon is not acting actually, so they're just measuring the heat flux between two containers, and then they can stop the heat flux, okay, or reverse the heat flux by using the demon. And the key result of this experiment that is actually, you see that the fact that the demon is processing information is actually heating, and they measure the heating, the heat that is dissipated by the demon, because actually the fact of processing the information needs some work, okay? Then there are other work on quantum system, so I will skip all of this and I go back to this slide, okay? So now let me discuss the Landauer principle. What the Landauer principle says is that any logical irreversible transformation of classical information is necessarily accompanied by the dissipation of at least a kBt log 2 of heat per lost bit, okay? And for example, logical irreversible transformations are, for example, several states of end-to-end or of circuits, but certainly the most irreversible is the erase operation, okay? Because of course, when you have erase your information, you cannot recover. The idea is this, the idea of reversibility in logical information is the fact that the knowledge of the output does not allow to know the state of the input, okay? So, so let me stick now to this, the most irreversible transformation, that is the reset operation, okay? And so so the Landauer principle is this. So for each eraser, you have to spend the kBt log 2, okay? Landauer principle is a certainly central result, but has been criticized, and but however, it has been tested in several experiments, although the criticism that has been done, okay? That honestly, we do not understand too much. But anyway, the question is how to reach Landauer's bound in experiment, and then the other question is, does any experimental feasible protocol allows us to reach this bound? Is there a strong connection with stochastic thermodynamics? These are the questions that we will go to discuss now, okay? So we follow Bellet, and to explain why the Landauer bound exists, okay? And so the idea of Bennett it goes back to the 1882, is the following. Suppose that I produce a memory, okay? That is just to a 2 wells potential, okay? And then you say that the left state is 0 and the right position is 1, okay? And then, of course, as in any measurement, the initial state can be 0, 1, okay? And then, okay, from a statistical point of view, as you have probability 1/2, then the entropy of the system is kb log 2. If you repeat the experiment many times, of course, you have only one particle. You have to repeat the experiment many times in order to, but so this is actually the case, and you start from this state. Now, you find a protocol, okay, any protocol that allows you to force the particle to be in the state 1 at the end of the protocol, okay? So at this point, if the state is 1, with probability 1, the entropy of the system is 0, okay? And thus the difference of entropy between the initial and final states is minus kb log 2, okay? And so it means that you have to do some work, And if you do this, the protocol is quasi-static. This will be minus TDS will be the amount the heat is changed with the heat bath. And is the energy variation is delta U. You see that the energy variation is delta U because the form of the potential of the end and the beginning and the end is the same. Okay, you see that the work and the heat has to be the same, and you need because of this that this quantity as KBT, KB2 log 2, and so the answer is that the minimum work is needed to erase the bit. Okay. So how can this protocol be experimentally realized? Okay. Okay, so again, we will use the famous optical trap that we already discussed. Okay, so I'll skip this because it's been already discussed. We are producing, for example, an harmonic potential. And if I put two beads, as I said already, I can have a B-harmonic potential as the one, sorry, a double well potential as the one produced there, okay? So now, as I said already, we have already seen this, and then, okay, this is typical case in which you have 2 KBT, you have the Kramers rate and so on, okay? And now you have to remember that I can play several games here because by playing I can for example change the intensity. I can also change, for example, the intensity of the two lasers in order, for example, to incline the depth to have the different depth of the two wells. Okay. So I now increase the power of the laser. Okay. And okay, so I have a barrier that is very high, larger than 10 kVt, okay? And so the first step, I reduce the barrier. Doing this, I reduce the intensity of the laser beam, okay? Then what I do, we gently incline the potential, okay? Here indeed, we didn't, for several technical reasons, we didn't change the intensity of the laser, but we introduced just a control, very control flow that it was pushing the particle on that. So you see that we're changing the probability distribution, and this is equivalent to incline the potential, okay? So you do this ramp that gently inclined the potential, okay? And this actually is done in a certain amount of time, okay? And then what you do, you stop pushing and you increase again the barrier and you trap the particle in there. You see, this is what was done when you start in 0, but if you see that the same occurs if you start in 1, okay? So you have realized what Bennett proposed, that is that you, independently on the initial position, you find the particle always in 1. So you have produced the resetting operation. And now, okay, this is just typical what is happening. This is a time record. You see that the particle is there, and then suddenly it jumps there. It remains, okay? And this, when you start, then you start from 1. Again, you see that there are events in that are actually producing negative events because the force is pushing in this direction and the particle move in the direction or the opposite direction. So giving exactly the negative work that we have discussed in these days, okay? Now, again, well, now you have already seen this. This system is again described by Langevin equations, but with the trapping potential plus an external force. We compute the work produced by the external force, and let us see what is happening. Okay. Of course, in order to increase the statistics, we do the two processes, 0, 1 goes in 1, 0, 1 goes in 0, in order to increase the statistic, and so. Okay, so you see that there are 2 points because so we have the pushing regime, okay, plus the point in which first I reduce and then I increase again the barrier, okay. You see that this is if it is done correctly at fast, but not too fast with respect to the relaxation time, you see this will give zero. We have checked this and is not a problem. The effect of reducing, increasing the barrier doesn't give any contribution. You have a question? Yes.
From the previous slide, so
yes,
where you're saying that from the two
this one or the one this one, okay, no.
potential energy plot. So where
this one, yeah, okay.
yeah, so you have not changed the intensity to change the
Yeah,
you have introduced the flow.
yeah.
So flows are usually global flows. So why only one of the minima are? I mean, flow should be for the whole slide.
Yeah, okay. It's equivalent to a flow because in order, if you introduce a flow, you have no control. It's very bad. Actually, we measure, we move the cell with the piezo, okay? So that was extremely well controlled, okay? So you see that is equivalent because the particle is trapped, you move the cell, and so you have introduced a force that is pushing. And the effect that if you measure correctly the viscosity, and then you know the speed, and so the measure of the force is extremely precise. Okay. Okay, so this. Okay. Okay. Now you see that. As I said, this term you need not to compute. Okay, then you see that this is the probability distribution of the work. Okay. Now you see again that this is the mean, this is the Landauer bound. Okay, that is there. And now you see that indeed there are a lot of negative fluctuations of this work. You see, you have these tails that goes to negative fluctuation, which actually correspond to those events that I've shown you before. Okay. And now what you do, I plot the mean values as a function of the time in which I did the protocol, mainly in which I moved the cell, applied the ramp, the fourth ramp that is here. Okay. And okay, this is what is happening. You see, this is the work or the heat that are equal because delta U at the end of the protocol is the same. Okay, you see that the slower you go, the more you go close to the Landauer bound. Okay, these are very slow cycle of 30 seconds, and now you see that you will always be above. Now, I will discuss this point later. It's not an error. It must be there for reason that you will see in a moment. Okay, you see that the important message, the work approaches the bound, but its values are always larger than kBT log 2. Okay. Now, why do you have this point that is below? And the reason is the following, that indeed there is another important quantity when you do this, the success rate, okay? That is the amount of time you find the particle in the good, in the good trap, and with respect to the number of tests that you have done. Because sometimes you find the particle in the wrong well, okay? And so this is typical in our system. The success rate was around 98%. Okay, and you see that actually the success rate can be changed by changing the maximum force that you have applied. Okay, the more you inclined in somehow. Okay, and the more the okay, then I will explain why we have not 100%, but this is just a technical issue. The important point that indeed you can modulate the success rate by changing the maximum force. Okay, and now you see that here, okay, this point, okay, is a small success rate, and this it goes below. And this is again is important information, because if you can generalize the Landauer bound as a function of the success rate, and the way of modifying it is just to add this entropy, that is the Shannon entropy of the system based on the success rate, which is a probability. And then what you see is easy to see from this expression that indeed, if the success rate is bad, okay, you don't gain any information in doing the protocol. That is, the uncertainty at the very beginning was 0.5, because you have 50% of probability of being on the right, on the left. If you have at the end of the protocol the same uncertainty, of course, the work that you need is 0. And this is what equality tells you, and also explain why, if you reduce the success rate, you can go below the Landauer bound. Okay. So then there is the question of the blue line. The blue line, it's another interesting point, because Sekimoto in 1997 asked a very nice question that was not never discussed before, which is very strange. And so the fact is the following: we know that when you, as we said several times, in order to get the free energy, okay, you have to do a quasi-static transformation. But of course, you do that in finite time. And the question that was asked by Sekimoto is, what is the correction if I do the transformation in a time tau, which is longer than the relaxation time of the system, but still limited, okay? And so it came out with this result that if you do a transformation on a time tau, you see that the information that you have on delta F should be as B over tau, where B, of course, depends on the system. And this is actually what is happening here. You see, because delta U is equal 0, delta F is only given by T delta S. And then you have to expect that indeed W goes as KT log 2 plus B of tau. And this is exactly what is going on, what is going on here, okay? Voilà, okay, so then the question I don't know, this is just a technical point. That is why we don't get 100% in our system. And the point is that our barrier is not sufficiently high. This, we have tested this with numerical simulation, because it was difficult to do the experiment. But in any case, you see that the fact that we are not 100% is just a defect of the experiment, that in which the two states are not well separated. Okay. So to summarize, our experimental results indicate that the thermodynamics limit to information eraser, the Landauer bound, can be approached in a quasi-static regime, but not exceeded. The asymptotic limit is reached in 1 over tau, and the fact that the success rate is smaller than 1 is due to the finite of the initial barrier. Okay, thermal fluctuations, you have seen, plays an important role, because you have negative events that actually allows you to reduce the amount of work of the mean. Okay, so what is happening? Okay, the experiment now, this is just an overview. The experiment has been repeated in many different systems, so I will not go on that. It's just for information that indeed there are many other experiments that has been done between 2012 and 2016. Okay, these are very complex experiments in different systems. I will not discuss this. Instead, I mean, that is in connection with what has been said during the other lectures, is the connection with the Landauer bound, the Janskinski equality. The fact of having actually a success rate that is not one allows us to understand much more this problem. If the success rate was one, that this kind of consideration cannot be done. Okay. So let me. We have seen that the Janskinski equality relates the work done in the system to the free energy difference. Okay. This was definition of the work that we used, and indeed we use this definition, but there is just a change of sign here because in the initial and final state F is 0, so there are no problems in using this. Will be this definition because we apply a constant force and not a constant displacement. Okay. The point is the following. You see that the delta U in this case, so the Hamiltonian of the system is somehow, so the conservative part of your equations is the same at the end of the protocols, at the beginning, at the end of the protocols. And so you are in trouble because I've shown to you that indeed delta F is changing of a KBT log 2. And so where the problem is? The problem is that you have to use an extension of this equation that was derived later by Vaikunthanathan and Janskinski. I don't know whether I pronounce correctly this name, but anyway, the idea is the following: that indeed, you are forcing the system in a situation that is not the equilibrium one. Why? And if you do this, what this generalized equation tells you that, okay, you have the exponential of the free energy, but there is a correction factor that is due to the fact that if at time tau the system is pushed in a distribution which is not the equilibrium distribution, then we have these corrections. Okay, let us see that this is exactly what is happening here. Okay, and I'll show you it's also by measurement. Okay, indeed. Let me see. Yes. Okay. So imagine that. Consider there is a erasure protocol. Okay. And 0, 1 going in 0, okay? If the final state is 0, then, okay, we have seen that the success rate is order 1, okay? And rho of equilibrium will be 1/2, okay? Because if the system goes at the end, okay, you have 2 well potential, the equilibrium distribution will be 1/2 on the side, okay? But indeed, so if I use delta F is equal 0, okay, so the non-entropic component of delta F is 0, and so what you have using using this generalized, the generalized equation, you see that delta F is 0, so I'm using this equation, okay. And so what you get that this is just, the work that you do is just 1/2 over R, okay? And so you see that indeed the work for going to 0 is log 2 log R, okay? So let us see indeed what you can separate the Janskinski equality in the work done if the particle makes jumps from 1 to 0, and the work done when the particle starts in the final state, okay? So W00, 0, okay? And now you see I have this prefactor 1/2 that appears there, okay? And then you see that the sum of the two has to give 1/2. And this is actually the case. You can do this experimentally, and you see that, well, of course, the error, the statistical error are very big, but you see that indeed this is the sum of the two, plus is the work M00, the work 10, and you see that the sum of the two, okay, goes around 1, okay. So and then, okay, let me do the other case. I will show you the connection with the Janskinski equality and Landauer bound. Suppose now that I consider the case in which the final state is 1 instead of 0, always doing this protocol, okay? And now you see that the probability is 1 minus R, that R was close to 1, this was close to 0, okay? And then rho equilibrium is equal 1. And now you see that this probability is just 1, this result of this integer, of this mean, is 1/2 over 1 minus R, okay? And so this means that the work going to 1 is log 2 plus log 1 minus R, okay? And what is happening is that if you take the mean of all the work, will be R when you have success rate, when you go to 0, you find the particle in the good position, and this component that appears 1 minus R times, okay, when the work done when the particle is in 1, so which is the wrong position. And now you see, if you develop this, you see that using the inequality that I have, you see that the work must be log 2 plus R log R and 1 minus R, which is the generalized Landauer's bound that I've shown you before. So this is a strong statement because it really allows you to connect the Landauer's bound to a thermodynamics quantity, to a thermodynamics equality that is the Janskinski equality. Okay? Do you have any questions? Yes.
Bring that. Erasure should only cost energy only when you do not know the initial bit
Sorry,
string.
I couldn't hear you.
Erasure should only cost energy if you
Yeah.
do not know the initial bit string, right? Because otherwise you can use like NOT gates, which are completely reversible. For resetting?
Not gate are, yes, it can be reversible.
If you have a
not gate can be completely reversible, yes.
Can be completely reversible.
Yeah, and then you do the zero
And then you
work.
can erase in some sense reversibly, and it should not cost any energy, right?
No, if you do not, is not you don't erase. What do you?
My
No.
point was.
No, because the point, if you erase, you have to bring your system in a complete state. Not is not an erasure process. Not is just you reverse the bit. That is what was 0 becomes 1. Okay, but this is completely reversible operation because I can do the reverse. Because this is not irreversible from informatic point of view, because the definition is that the knowledge of the output does not allow to know the state of the input, okay? And the not is completely defined. Because if I have 1 at the output, I know that there was 0 at the input, so it's reversible from this definition.
So if you have a complete knowledge of the initial state.
Look, I'll give you the simplest example. Take an end, okay? Take an end, okay? And let us do the truth table of an end, okay? You have A, B, okay? And then you have the output, okay? So you have 1, 1, if you have an end, will be give 1, okay? 0, 1 will be give 0. 0, 1, 0 will be 0, okay? And 0, 0 will be 0, okay? So what is reversible and what is irreversible here? You see that this is completely reversible, okay? Because the knowledge of the output allows you to know the input. But these three are irreversible operation, because if you want to recover the energy that has been used in order to go into this state, you have to pay. No, anyway, it's not possible actually, because it could be one of the three, okay? This is the point. Instead, the knot, if you do the truth table, you see that it's completely reversible, because there is only one state at the end, at the entrance, okay? Other questions? Okay. So, okay, this is the general, okay, this Landauer equality. Oh, no, okay, this is just to show that indeed, if you compute using the generalized statistical equality, you see that all the points actually of the same series goes on the Landauer bound within experimental errors, okay? These are obtained with, okay. This is, okay, yes. How much time do I have? Not too much. Anyway, we can go to just to make a short discussion. No, but I started later, no? Yes. Yeah. Okay. So let me discuss this point. So what you can do, how much I can approach the Landauer's bound in short times, okay? The first who asked this question was Aurel and co-workers in 2012. Indeed, the question that they ask, suppose that I have a finite time, what is the protocol that allows us to minimize the work that is needed in order to commute the system, okay? And okay, you can do this, but you can go into also another system which is quite different, okay? And you use, for example, instead of doing the experiment with colloids, you can do, for example, with the micromechanical actuator, okay? And okay, I'll skip all the experimental details, but what is happening here is that by doing this feedback that is quite similar to the Maxwell demon anyway, it allows you to construct this potential, okay, where S is just the sign of the argument of the function, okay. And so you have a B-harmonic potential that actually you can change by changing, for example, the control very well by changing the voltage that we apply, for example, between the tip of the laser of the cantilever and the bottom surface. Okay. So here is typically the spectrum when the system is free rounding, but you see that this is just the potential that has been measured starting from the probability distribution function as before. So you see that now this is a B-harmonic potential that it allows us to repeat the Landauer bound. And now what we did was a completely different protocol with 100% success rate. And the protocol is the following. You start from the double well, you can be either in 0 or in 1, okay? Then you merge the two wells in a single one, okay? And then once you have put the particle there, you move slowly the particle here in the initial position, okay? You make the second well appear there, and now you see that the particle stays, for example, in 0, okay? And now you see that this protocol cannot fade, okay? Suppose that is sufficiently high barrier, okay? And now you see that you can you can explore the work as a function of time. This is doing the merging state, so the system is doing work. Okay, then and this is just you can really see this is just the entropic work that is needed, and then you stop there, and then you slowly move, okay, the particle. This is the second part where you move the particle to go back to the initial state. Okay, and now you see that indeed all the work, this is very interesting, because you see that all the work is mainly done during the entropic phase, where indeed the entropic part is just when you collapse the two wells in a single one. Okay, and okay. So, and then you see that when you move there, as it is done quasi-statically, you see that the work is close to zero, because this is done very, very slowly, okay? Although this is done very slowly also, but the point is that you are changing the entropy of the system. And now, I mean, plotting thing as before, you see that again, by changing the speed of the protocol, wow. Why? This, okay. So you see that again, you have a 1 over tau behavior as in the other case. But what I wanted to point out, the fact that you have changed the time scales of the system going into an inertial regime where inertia is important, you see you have changed the time scales of the system of almost 2 orders of magnitude. And now you see that first of all, the error are smaller because the system is faster, so you can average much faster. And then you see that this were the original plot that I've shown you before, that you were order of 40 seconds in order to be close to the Landauer bound. And now you see that in a few milliseconds, you can reach the Landauer bound. So the answer to the question, I mean, it is possible using underdamped systems. Okay. So the main message of all this of all this talk is the following: that Maxwell demon allows us to produce energy from information. Information is the minimum energy in order to be processed, because the idea is that the Maxwell, the demon is observing the system, but has a certainly finite memory. And so at a certain point, he has to erase his memory in order to start the process again. Okay, so, and what the main important message that I already mentioned is that the energy gain from information is smaller equal than the processing energy. And the demon of course cannot overcome the principle, the second principle, in the sense that in any case the energy that you need in order to analyze the information, okay, is larger than the energy that you produce from your system. This is okay. This is the possible applications. Okay, we know that today that there is a lot of energy that is used in computation. Okay, this is the computation, the computation energy per flops. This is in flops per watt. Okay, and this is a function of time. This is a function of year. Okay. And what is interesting, you can extrapolate this line, okay? And it's interesting to see that if you continue like this, you will reach the Landauer bound around 2050, okay? Of course, I mean, probably this curve will bend, but sure, at this point, we could not do better than this, because this is the physical limit for the information. Okay, so this is an interesting point. Of course, as I said, this small amount of kBT log 2 play already an important role in feedback system, for example, in biological system. Okay, these are the person who collaborate with me on this subject. Okay, and then these are some general conclusions. But before doing this, as I have still some time, I will do a blackboard exercise again, and then I will discuss this as the end, okay? So let me do, you had an example exactly on the poster of Rafna, and I do a small exercise in order to understand what people does about information and the Maxwell demon. So the other case, the Toyabe experiment that I have shown to you before. So as I've already shown in the first in the other slides, okay, I can write that the mean work done by the system is larger than delta F, okay, minus I, okay. And now, and this is coming from Jensen inequality that tells you that exponential minus delta mu plus delta F minus I, okay? The mean of that is equal 1, okay? And now let me do the following exercise taken from a work of Sagawa and the work of Sagawa and co-workers. So the idea is the following. Yes, I want just to do this. Suppose that I have a particle, okay, which is trapped in an harmonic potential, okay, and then I construct the following. So the particles start in 0, okay. This is X. This is the potential, okay. And then I want to move the particle, okay, without doing a minimum work. And for example, I can do blindly by taking this trap, as we saw in the example of yesterday, by moving this at constant velocity, okay? But this I'm paying energy, okay? And so the demon allows me to do without actually gaining energy with respect to the system. So the idea is the following. Suppose that I call this L, okay? And this 2L. Okay. And now the particle is moving inside this potential. Okay. So what is happening? The particle at a certain point moves in there. Okay. Oscillates because of Brownian fluctuations. Okay. And at a certain point, and then I look at the system. Okay. And I make the following. The following choice. Okay, I have a variable, the feedback variable that I call y. Okay, and then I will tell you what it is. Actually, is the measure of the position of x. Okay, y is the measure of the feedback. Okay, so if you want the feedback signal, and if the feedback signal y, okay, which is the measure of x, okay, x is the position of the particle, okay, and y is the signal of the feedback, okay. Now, if the signal, if y, the measure, give me smaller than L, I do nothing, okay, and if the particle, when I do my measurement, okay, if the particle is above L, I shift, okay? And now you see that is a very smart method, because the particle, if the particle is there and I shift when the particle is there, you see that I actually gain this amount of energy because the particle is just changing its potential, okay? And the work that I'm doing at each step is, of course, the difference of the two potential, and is the potential difference, which is minus 2k Lx. Okay, this is easy to compute. Okay, so now you're doing this work that again is a fluctuating quantity. Okay, and what is happening? You can show that now. Suppose I'm doing some hypotheses on the quality of my feedback system. Okay, and I say that I have some measurement noise. Okay, so my information is somehow perturbed by the measuring noise. Okay, and so I can say that the joint probability Px and y is something, okay, don't put the normalization factor, and then this is just exponential, okay, of minus x x square. X is the position of the beam. X will be 0 here to L there, okay, and this will be 2s, standard deviation of the fluctuations, and then I have another terms that is given by the measure of the system, okay, of 2n, okay. So this is the joint probability that I have, and this is tell that I have a variance in the measurement, so I'm making mistakes when each time I measure the position of the particle, okay? And then I can introduce information that is mutual information now. It is, again, is similar to the information given by, the mean value will be the same of x and y, okay, divided p of x and p of y, that you can derive from there, integrating this one in y and this one in x, okay? And now you see that the game is done, because, sorry, in this case will be, the work will be this one when y is larger than L, and of course the work will be 0 if y is smaller than L, okay? So now you see that the game is done, because delta f in this case is 0, okay? And so this integral, I have to stop. So I go on the other side, okay? So, yes, I write here, okay? So the integral, the Janskinski, the generalized Janskinski equality, which contains information, you see is a very nice idea, because what I have, I write minus I, okay? And this I have to integrate this on p dx and y in dx dy, okay? And now you see that by my definition of information based on the mutual information, okay, that is a px of y, you see that this system goes, I can replace this, and then you see is minus w, okay? And then, okay, it's easy to see that what remains is p of x, py, in dx dy. Okay, and then you see that this guy is for sure equal 1, because py for the normalization of that is 1, but then now the integral of a minus w is done over x. You see that w is a function of only of x, and so this guy is equal 1. Okay. And so this actually shows that in this simple example, this equality is totally satisfied, provided that the information is defined in the correct way. Okay. So as my time is almost over, let me discuss some. So do you have any questions on this example? No? Okay. So. I have to share. There is. Okay, sure. Okay. Good. Okay, and then shift it back. Okay, so let me give you some general conclusions. Okay, so I hope that I convince you that the stochastic thermodynamics is a useful tool to characterize out of equilibrium system. Somehow it extends the law of thermodynamics to fluctuation in mesoscopic and microscopic system. We have seen that the fluctuation, okay, see, this we have not seen because we have no time, that fluctuation theorems, the Jansky and Crookes equality can be successfully used in several different systems. I didn't show you the fact that how the fluctuation theorem, it's okay. I was thinking to fluctuation dissipation theorem that I don't discuss. So anyway, so fluctuation theorem and the Jansky and Crookes equality can be successfully used in several different systems. And I have discussed also the connection between thermodynamics and information theory. What I did not discuss is the modified fluctuation dissipation theorem in non-equilibrium steady state, because will allow us to, we'll need a long discussion about that. The uncertainty relations that fix several limits, for example, for the efficiency of micromotors, the efficiency of maximum power of micromotors, that interesting aspect. And what I didn't discuss at all are the quantum aspects of all this system. Okay, I hope that I gave you an overview of these subjects. Much of what I said can be found in an article that I wrote in PRX in 2017, where all this talk is based on. Okay, and so I thank you for your attention.
Yeah, thank you, Professor, for the wonderful talk. Now the floor is open for question and answer. So if you have any question.
Okay.
Let's thank the speaker for the wonderful talk again.